Work? Okay, we're moving on with the springy.
I forgot what sign.
Okay. Woo. That was a lot of work. No, it doesn't.
It does.
Nope.
Yes, it does.
Nope. Nope.
Even, well, Mr. Hall, like this, do you qualify biking up going to Sun Road as hard work?
No, that's recreation.
Okay. Oh, look, I saw a video, so let me do it anymore.
Oh my.
Okay,
oh
so back to this thingy. So the next page, we covered the horizontal mass spring system, right? So this one's going to be pretty quick actually, because we're gonna make a realization on this one that is really important. So you have a spring. So the question says initially the spring is like this, right? And then it says we add a mass to the spring, and it is at equilibrium, right? So the first thing we want to look at is the question says what. So read the top there. What letter are we assigning to that initial distance that it's stretched out?
No, one.
X.
What?
It's Y. So
Oh, well, no.
stage one, you put it on. Stage two, it stretches to equilibrium. So some distance Y, right? And this is equilibrium. Right? And then it says we're going to pull it an extra distance. Now, what's the extra distance we pull it? X. Okay? Does the picture make sense? So that's what you see when you do it with the real one. So, okay, it starts off like this. You add the spring on. So the distance from where it is right now to here is called Y. And then you can stretch an additional distance X. And if you let it go, it oscillates. Okay? So it's kind of hard to hold it there. Anything for the Twitch followers. Okay, so the first question is how much energy is stored in this spring right here?
Oh, can you do equilibrium plus the amount of distance in X and like find them together? Like K equals 1.
You're overcomplicating it. So what's the formula for energy stored in a spring? 1/2 kx squared. But that's when X, the formula is 1/2 kx squared when X is the displacement. What's the displacement? What's the total amount of stretchy that the spring has done right now? X plus Y. So it'd be 1/2 K times the total stretch squared. My computer just did something. What was that? Did it say stream dead? No, seems to be still be working. I won't get my 100 bits. What will I do? Today we'll just be playing that one game. I drive around. GTA 5. Okay, so B. So that might be a little alarming because you may go, oh, that's kind of complicated, right? But the key here is the next step is it says just as the block is released, what's the net force and what's the acceleration and stuff like that. So let's look at this moment in time here. Let's draw the force diagram. How much force pulls the block down?
MG.
Mg. Very good. And then how much force pulls the block up?
AXY squared. MKXY squared.
No, would just be X.
So for a spring, F equals Kx is the formula, right? And remember, when you write it that way, X represents the displacement. So how much has the spring been displaced?
X plus Y.
X plus Y. So it's K times the quantity X plus 1. You feel okay about that? So I could say that the net force is equal to, now which one's going to be bigger? The up or the down? The up. That's the direction it's going to go. So it would be K times X plus Y minus mg. But wait, there's some sneaky stuff in here. We can make that look a lot nicer. Because look back to this moment when it was in equilibrium. What would the force diagram look like when it's in equilibrium? It'd be equal, it'd be balanced. So in this state, I'd have mg, and what would be balancing him out? K times y. So therefore, ky and mg are the same size. You feel okay about that? So therefore, over here, when I have, so if I distribute this, kx plus ky minus mg, wait a second, this term and this term are the same size. So they cancel bobancely, and we get this really nice result, which is, so what does that tell us? This is a big result here.
The
Colin's
displacement
got an
has
answer. Wait,
equal-
Colin, what's your answer?
Is it that the, so the like net force of the system is dependent on how far you displace the spring past equilibrium?
Exactly, yeah.
So equilibrium is basically zero net force.
Exactly. Well, yeah, there's that. So it's telling us, yeah, that this y does not really matter. It doesn't really matter how far the spring had been stretched when you set up the system. And that tells us, look at number 1, that tells us the system's going to behave identically to the first one we did, which is weird because you might think, well, this also tells you something else. What if we turned up gravity or turned down gravity? Say you have the dial on gravity.
It would change Y.
It would change y, but it would have no effect on the forces involved in the system because what happens is gravity, the effects of gravity, sure, they definitely matter, but as far as like they're there, but they're canceled out. Once the spring hits equilibrium, it's as if gravity has been taken out of the equation. Well, literally, it's been taken out of the equation. It's no longer relevant. So anyway. So what does this tell us about the acceleration? So if I say F net is ma, so here's where everything floweth through here now. We will hopefully be like, wait a second. This is the same thing here. You're like, wait a second. You're telling me the net force at that initial state's the same as before. Well, then so the acceleration. And since the block is traveling from this state into what's the net force here? 0. So do you see how it's identical? Not to belabor the point, but okay. So then, therefore, there's the net force at that position. There's the acceleration at that position. And it does ask what's the velocity when first released? What's the velocity when you first release it? 0. That's nice. And then for part C, Mr. Bill's voice is so booming, kind of gel.
He scared me on numerous occasions.
I don't think my voice can ever be that booming. It's sad.
Mr. Hall, however, when you're writing in like our Mr. Bill's class, we can hear you writing on the whiteboard.
The squeaks?
No, just you hitting it, like it's the tap, like
We're
burn.
kind of like bonk.
Yeah, like you can hear it.
Good. Okay, so then C says, as you're passing through equilibrium. Now here's the thing, you can do it's a pretty complicated, to get it all to work out, talking about energy, it's fairly involved, and I think it's more elegant to just notice that this system is identical to the first system, and then just use that result from before. So what's gonna be, as you're passing through equilibrium, what's the net force?
0.
0. What's the acceleration? 0.
Okay.
Right? Because at equilibrium, the forces are balanced, as we know, which tells us the net force. If net force is 0, acceleration is always 0, but the velocity is certainly non-zero. And what result did we get earlier for the velocity?
It's the maximum distance sooner reach.
It was square root of k over m multiplied by x. Kind of a weird, well, these are all the answer, but
And isn't that at that point is the fastest velocity?
yes, that's the fastest you're going to see it going. So an acceleration is, in a system like this, you hit the maximum velocity when the acceleration is the smallest, which can be a little counterintuitive because I think, the way we use words like acceleration in common parlance confuses people. A lot of times we'll say acceleration when we really mean velocity. Okay, and then so for D, what are so again, same principle as before. I'm going to be like, well, okay, then I can infer that the frequency is going to be identical. And the period would be identical to the previous one. Yeah, well, it might be a little bit shifted just because of how we're starting it off. I think in the previous one, we started off with a positive displacement, which meant that the initial acceleration was negative. Whereas here, we're starting off, assuming we call this position 0, which we should, equilibrium pretty much always, you want to call that 0. Not that you have to, you could call this 0. You'd have like a sine wave on top of the axis. Anyway. So let's go position. Now position is a y value now, so I'm going to call this, we'll just call this position. Position versus time, we're going to have velocity versus time, and we're going to have acceleration versus time. Okay, so with position graph, what's our initial, so at time 0, and time 0 is going to be the moment when you release it, where's the position? Positive or negative?
Negative.
Negative. So I'm calling this 0. That's going to be my 0. And so, yeah, we're going to start off with negative position. And what's going to do, it's going to go up and then back down and then repeat that process. So that curve, that graph would look like this. Something like that. Does that make sense?
Mm-hmm.
That's part of a sine graph or a cosine graph. You either think of it as a shifted sine graph or a flipped cosine graph. The velocity function, what does velocity start off at? 0. And does it start off by going positive velocity? Or does start off by going negative velocity.
Positive.
Starts by going up. So yeah, it's going to do one cycle looks like this. There we go. And then for acceleration. Acceleration starts off positive. So one cycle looks something like that. And there we go.
Mr. Paul,
What up?
this is an observation made. Will the position and the acceleration graphs be opposites of each other? Like his, so it was on number on the first one as well.
I think so. Want some quackalus?
Yes.
Oh,
That's fire up in calculus.
Well, take either a sine or a cosine graph, right? The derivative of sine is cosine, the derivative of cosine is negative sine. So if this is position, velocity, acceleration, makes sense. Or what if you start with cosine? Derivative of cosine is negative sine, derivative of negative sine is negative cosine, same thing, they're gonna be opposites of each other. So, good observation. Yeah. You could also think of it as in terms of two shifts. A lot of times what they'll talk about in this, they'll talk about a phase shift of how these are shifted. So take a sine graph and then the shifted version is the velocity. Shifted again for the acceleration. Okay, guys. So the rest of these questions, at least until we're gonna do pendulums pretty soon here. But the rest of these questions are just about mass spring systems. That's what this is called, a mass and spring system. We can answer one or two together, but the rest, I hope, are just going to be fairly straightforward. Most of the questions just come down to like, can you manipulate this? Can you understand how this works, this equation? You want to do the first one together? If you have a mass spring system that oscillates at 3 hertz and you double the mass, what's going to be the new frequency of the system? So some things to think about are, can you visualize 3 hertz? What does 3 hertz look like? Not like you have to know that for this question, but it's good practice. Is 3 hertz kind of slow or kind of fast? Well, I guess it depends on your context. For like a motor in a vehicle, that's very slow. Like if your wheel was only spinning 3 times per second, that's not very fast. But
You're running 3 hertz.
so yeah, a 3 hertz. So if it was a mass on a spring, I'll try to do it 3 cycles per second. So something like that. Right? I'm trying to do 3 full cycles every second. So that's pretty quick. This, if I let this one go, this is definitely not 3 hertz. This might be like 1, 2. This is about 1 hertz, I'd say roughly. Maybe 1 point something. Maybe it's a little bit faster than 1 cycle per second. Okay, so anyway, which formula should I investigate or should I look at for this one? The frequency,
Yes.
right? So the frequency of a mass spring system is 1 over 2 pi times the square root of k over m. And so suppose that this initially was 3. Who knows the answer to this, by the way? What's going to happen if you double the mass? What would the new frequency be?
Smaller.
Smaller, yeah.
It would be smaller by a factor of root 2. So what you do, so let's say if this is the old frequency, it's the same thing we've been doing all year. The new frequency would be 1 over this times. Notice how everything is the same except for that 2. So what's to stop me from pulling this root 2 out of the expression? Is making sense? Like that. And so if this was 3, right? If the old frequency was 3 hertz, then this right here is 3, isn't it? So the answer would be. That make sense, or? we confused, or does that make sense? Do you guys see how it's the same as what we've been doing all year, as far as like comparing to? It was like, oh, if the frictionless block reaches a velocity of v, what's the velocity reached by the hollow sphere? That kind of question. No questions? Are we sure? Okay. How about number 4? If you have a mass spring harmonic oscillator and the spring constant is 100, and you wanted to double the frequency, so same equation we're looking at, how can we double the frequency by changing the K value?
Make the K value less, like weaker.
What, Aiden?
4 times bigger?
Oh, yeah.
So for 4, yeah, you're like, okay, if my old frequency is the same thing. You know, a lot of people are thrown off by the fact that there's like a constant in here, this 2 pi. But do you see why that doesn't really matter, since like the old and the new, they both have that same constant. So when you're comparing them, like they both have it. So anyway, if this one's okay, so if this equaled 100, then hopefully it makes sense that if I want to make my new frequency equal to 200, well, how do I double that? I've got to make this 4 times bigger. Hello, Mr. Thompson. Good morning.
See Julia Sauerwein and Caleb.
Dope. So you can see that if you put a 4 in here, the square root of 4, I know, Trenton, it's very,
I'm here.
it's very exciting. So square root of 4 would make this double as big, twice as big. So you can, and if you're still confused, plug in some numbers, you'll see that it works out that way. Okay, and we'll go over 6 as an example as well. And then from there, I don't know, you'll have 10, 15 minutes to just knock out a few on your own. So look at 6. It says this graph shows position versus time on the vertical axis. Position versus time, where position's on the vertical axis and time is on the horizontal axis. Over an interval of 6 seconds for a mass spring harmonic oscillator with 5 kilogram mass. Find the spring constant of the spring. So how will we do this? What do we do?
We need to, hold on.
6 seconds.
This is 6 seconds, right? So what's the graph telling us? What quantity is the graph giving us information about?
Well, we know the time, and then we also know the mass.
We know the mass. So if this is the position versus time, I'll give you a hint. What? The period. See? So this tells us that one cycle, so to go up, down, and back to the starting position, takes 3 seconds. So this graph is telling us that the system has a 3-second period. Maybe you were thinking, well, wait a second. I thought of it like this. I thought of it as it's telling us the frequency. Because the frequency would be number of cycles per second. And he did 1, 2 cycles over 6-second period. So the frequency is 1/3. Who's correct? They're both correct, right? A period of 3 and a frequency of 1/3 are same z wavelengths. So, I don't know, let's use this formula, I guess. Although, if you're solving for k, which formula is nicer? Probably this one, because k is on top, right? Yes?
Yes.
I'm so sorry, Kate. Class is almost over, don't worry. Oh, you guys. Okay, let's use the top one then. How are we feeling algebraically to deal with this? Confident or not confident?
Pretty good.
Okay, I'm gonna review it here. So if anyone's not 100% confident, so what's the frequency? 1/3. Very good. So the first thing I do is just replace all the symbols with the known values. What's the K value? That's what we're solving for. What's the M? 5. So step 1 is to make him go away. Multiply both sides by 2 pi.
And square root.
Not square root. Square both sides. Make sure you're squaring this whole thing. So when you're using a calculator, put that in parentheses. And then lastly, multiply both sides by 5. So. And hopefully it's obvious enough that that's not going to, I mean, that's a correct number, but it makes a lot more sense to express a K value in like a decimal. Okay, so, yes.
Do you want to take that answer out or like make it a decimal or do you want to leave it like that?
Make it a decimal. So you should get something in the ballpark of 20, maybe 21, maybe it's.
29.
Wow. How does it know? That's what I wonder about, right, guys? Right?
The Max Martin credit is
It's kind of genius.
absolute intellect.
Such a high intellect.
He was so far ahead of our
It's meme
time.
numbers. It's like the ancient sacred crypts of the Macedonian soldiers, right, Kate? The Don Alverzo's brass monkeys. Okay, guys, I can't handle the excitement anymore. You guys are you're going crazy, especially Trenton. He's bursting.
What?